morning. Today we are going to see enabling technologies for wireless sensor networks. The building of wireless sensor networks has only become possible with some fundamental advances in enabling technologies. First one is hardware design. First and foremost among these technology is the miniaturization of hardware. Smaller feature sizes in chips have driven down the power consumption of the basic component of a sensor node to a level that the constructions of WSNs can be contemplated. This is particularly relevant to microcontrollers and memory chips such as, but also the radio modems responsible for wireless communication have become much more energy efficient. Reduced chip size and improved energy efficiency is accompanied by reduced cost, which is necessary to make redundant deployment of nodes affordable. Energy consumption. The sensor nodes consume the power for important three functional domains such as sensing, communication, and data processing. Typically, sensors are powered through batteries, which must be either replaced or recharged when depleted. For non-rechargeable batteries, a sensor node should be able to operate until either its mission time has passed or the battery can be replaced. The length of the mission time depends on the type of application. A sensor node also has a device for energy scavenging. Energy scavenging, known as power harvesting or energy harvesting or ambient power, is the process by which energy is derived from external sources, captured and stored for small wireless autonomous devices like those used in wearable electronics and wireless sensors network. Such a concept requires the battery to be efficiently chargeable with small amounts of current, which is not a standard ability. Classical energy consumption mode. An classical energy consumption model. An energy consumption model for sensors based on the observation that the energy consumption would likely be dominated by the data communication subsystem. This following table reproduces their model. The energy level is mentioned by joules. Modeling energy consumption during transmission. The energy consumed by the transmitter is due to two sources. One part is due to RF signal generation, which mostly depends on chosen modulation and target distance, and hence on the transmission part, PTX, that is the power radiated by an antenna. A second part is due to electronic components necessary for frequency synthesis, frequency conversion, filters, and so on. These costs are basically constant. One of the most crucial decisions when transmitting a packet is thus the choice of PTX. Let us assume that desired transmission power PTX is known. The transmitted power is generated by the amplifier of a transmitter. Its own power consumption PM depends on the architecture, but for most of them, their consumed power depends on the power they are to generate. In the most simplistic models, these two values are proportional to each other, but this is an oversimplification. A more realistic model assumes that a certain constant power level is always required irrespective of radiated power plus a proportional offset. P amp equal to alpha amp plus beta amp PTX, where alpha amp and beta amp are constants depending on process technology and amplifier architecture. Software. Energy is the scarcest resource of WSN nodes and it determines the lifetime of WSNs. WSNs may be deployed in large number in various environments, including remote and hostile regions, where ADA communications are a key component. For this reason, algorithms and protocols need to address the following issues: increased lifespan, robustness and fault tolerance, self-configuration, lifetime maximization. Energy power consumption of the sensing device should be minimized and sensor nodes should be energy efficient since their limited energy resource determines their lifetime. To conserve power, wireless sensor nodes normally power off both the radio transmitter and the receiver when not in use. Then routing protocols. Wireless sensor networks are composed of low energy, small size, and low range unattended sensor nodes. Recently, it has been observed that by periodically timing, turning on and off the sensing and communication capabilities of sensor nodes, we can significantly reduce the active time and thus prolong network lifetime. However, this duty cycling may result in high network latency, routing overhead, and neighbor discovery delays due to asynchronous sleep and wake up scheduling. These limitations call for a countermeasure for duty cycled wireless sensor networks, which would minimize routing information, routing traffic load, and energy consumption. Operating systems. Operating systems for wireless sensor network nodes are typically less complex than general purpose operating systems. They more strongly resemble embedded systems for two reasons. First, wireless sensor networks are typically deployed with a particular application in mind rather than as a general platform. Second, a need for low cost and low power leads most wireless sensor nodes to have low power microcontrollers, ensuring that mechanisms such as virtual memory are either unnecessary or too expensive to implement. Thank you.